Değerli katılımcılar, sevgili arkadaşlar, bizi tüm sosyal medya platformları üzerinden izleyen bilim dostu, bilgisever, güzel insanlar. Herkese iyi akşamlar. TÜBİTAK Temel Bilimler Araştırma Enstitüsü, bilimin ufukları kapsamında sürdürdüğü araştırma ve eğitim faaliyetlerinin ayrılmaz bir parçası olarak uluslararası düzeyde ilham verici seminerler serisi düzenlemektedir. Temel bilimin çeşitli alanları ile disiplinler arası alanları kapsayan ve ülkemizin ve dünyanın dört bir yanında ilgi odağına çevrilen bu etkinlikler en üst düzey ve yenilikçi bilgilerin tartışıldığı ortamlardır. Bu etkinlikler aynı zamanda bilimde ilerlemenin klasik yolunu en iyi olanları dinlemek, onlardan öğrenmek, daha sonra kendi yolunda ilerlemek gayesini aydınlatmaktadır. Bu akşam yine bu düşüncelerle ve enstitümüzün kimya bilimleri seminer serisi kapsamında bir güzel bölüm daha gerçekleştirmek üzere bir araya gelmiş bulunmaktayız. Ben de her zaman olduğu gibi yine bu vesileyle hepinizi saygı ve sevgiyle selamlıyorum. Günümüzde temel bilimin en önemli başarılarından biri, İnsanoğlunun atomistik düzeni manipüle etme kabiliyetine kavuşmuş olmasıdır. Bu durumun bir sonucu olarak örneğin atomlar arası mesafelerin ve kafes geometrisinin sabit olduğu atomik ve moleküler kristalların aksine tasarımcı atomlardan oluşan nano kristal diziler sürekli olarak ayarlanabilen özelliklere sahip nesnelerdir. Nano kristallar ve nano kristal düzenekler istenen elektronik, optik, manyetik ve katalitik özelliklere sahip 2 ve 3 boyutlu malzemelerin tasarlanması için çok yönlü bir platform sunmaktadır. Bu durum endüstriyel ve teknolojik alanlarda yeni açılımlar yaratacak, yeni yarı iletken kuantum noktaların ve diğer yeni modüler malzemelerin geniş uygulamalarına yol açmaktadır. Bu akşam bu konuları kimya bilimleri perspektifinden ve konunun dünyaca ünlü uzmanı ABD'deki Chicago Üniversitesi'nden Profesör Dmitri Talapin'den dinleyeceğiz. Son derece değerli bir bilim insanı olan Dmitri Talapin, malzeme tasarımına modüler bir yaklaşım konulu bir konuşma yapacaktır. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear participants, dear colleagues and friends, hello everyone and good evening. It is my pleasure to welcome all of you for this episode of the Chemical Sciences Seminar Series of TÜBİTAK Research Institute for Fundamental Sciences, with the participation of Professor Dmitry Talapin from the University of Chicago in the United States. Professor Dmitry Talapin is a distinguished scientist and world-class expert in the field. He is going to give a great talk entitled The Modular Approach to Materials Design. At the end of the talk, we will have Q&A session. Please ask questions by sending a message through the chat button of the Zoom platform or just by raising hand. Dmitry Talapin is the Ernest David Burton Distinguished Service Professor in the Department of Chemistry, the Pritzker School of Molecular Engineering at the University of Chicago. Dmitry Talapin's group has broad expertise in synthesis, self-assembly, surface chemistry, and device applications of inorganic nanomaterials. His research interests lie in the development of novel functional materials through the assembly of rationally designed nanoscale and molecular components. Dmitry was born in Soviet Union and grew up in Belarus, received a doctorate degree from the University of Hamburg, Germany in 2002, followed by postdoctoral work at the IBM Watson Research Center. From 2005 to 2007, He was a staff scientist at the Molecular Foundry at Lawrence Berkeley National Laboratory, and finally joined the faculty to the University of Chicago in 2007. Professor Dmitry Talapin has received a number of honors and awards, including IBM Invention Achievement Award, NSF Career Award, Material Research Society Outstanding Young Investigator Award, American Chemical Society Akron Award, Inorganic Nanoscience Award, and many others. He's a fellow of the Royal Society of Chemistry, fellow of the Institute of Molecular Engineering. With this, I want to invite Professor Dmitry Talapin to the stage to begin his talk. Dmitry, good morning.
Good morning, good evening. Thank you for the opportunity to present our work, and let me share screen and tell you about the research that we've been doing recently, and the work that I will be talking about has been done mostly at the University of Chicago, which is a beautiful university, one of the world top research universities in physical sciences and many other aspects of human knowledge. And our outline for today will be largely focused on three topics. First, I plan to talk about or discuss the different chemical approaches that my group has been exploring to achieve atomic or come one step closer towards the atomic precision for materials design at the nanoscale, for nanoscale engineering. And second topic will be more also broad discussion of what we can and what we cannot synthesize in solution. And the third topic is, I will keep you puzzled for a moment. Now, let me, to set the stage for our discussion, let me talk about one, draw an analogy that I noticed some time ago and I found it very interesting and important, is that materials that I will be talking about, or more specifically inorganic nanomaterials, are close cousin to organic macromolecules. And in many ways, in terms of applications, in terms of fundamental principles governing their synthesis and evolution, we can learn from the work that has been done previously in design of polymers. And probably one of the important and fundamental questions with design of macromolecular systems was, to what degree can we control synthesis of polymers? And it was a big intellectual leap for chemistry community to move from or accept that we can have something, materials with no atomic precision, but still very useful and understandable. But then in the later decades, a few decades, organic chemists started playing with ideas, how can they bring atomic precision even to such giant molecules like polymers? With nanocrystals that are built of hundreds of atoms, we can now design, we come into same questions. So, and let me show you a video of a typical synthesis of colloidal nanoparticles. And we have two solutions, one in the syringe, one in the flask, mix them together, they change color, and in a few minutes we have nanomaterials. And a lot of important and complex phenomena are taking place during these few minutes, or sometimes few seconds. First, our molecular precursors, our molecules react and go through the very complex nucleation process. And then after we nucleate a new phase, and this new phase can be a metal, a semiconductor, a magnetic material, this phase evolves by growing into adding units, molecular units to the growing crystal, and just keep increasing in size. And at some point, when we have very small molecules, we can isolate small crystals, we call them clusters, with true atomic precision. But when we move past certain size, typically hundreds of atoms, we lose ability to control this material matter with atomic precision. So just adding a unit, a structural unit, removing structural unit does not change free energy or chemical potential, and we cannot use thermodynamics to do it. Pretty much same problem as with polymers. So we started thinking about how this approach can be dealt with, or if we can bring atomic precision to the synthesis of huge, like thousands, tens of thousands of atoms, materials, and nanomaterials. And first, we should look at the nucleation event. So nucleation is a very difficult and not fully understood process, but phenomenologically, it can be described quite well within the framework of classical nucleation theory, where if you have a homogeneous nucleation of a new phase, it's a competition of two energy scales. It's a competition of energy, surface energy that you need to pay to generate a new phase and separate it with surface from the rest of the system. But at the same time, your gain, energy gain, is that you generate a more thermodynamically stable phase. And this competition of surface scaling versus volume scaling give you a very characteristic effect of nucleation barrier and critical nucleus. And in the recent years, there were several interesting developments along this line where it has been first noticed by the team led by David Norris at ETH Zurich, where if in the pre-critical regime, the system can undergo interesting fluctuation, can undergo fluctuations that kind of force the pre-critical nucleus into anisotropic shape, and then the system can choose two different nucleation pathways. One is to grow more spherical crystal by growing like two-dimensional layers, one by one, or by growing like stripes, narrow stripes, which are more like a one-dimensional nucleation. And we generalized this approach and constructed potential energy surfaces describing this effect of nucleation in the formation of anisotropic nuclei. And we have shown that this effect, that in addition to classical nucleation barriers that described by classical nucleation theory, there are also this potential energy surface has pathways or valleys that lead to metastable products that, and these products can be atomically precise, like wires or two-dimensional platelets, or if you have enough energy to climb full activation barrier, you can grow to three-dimensional crystals. And it can be demonstrated by solution synthesis or fine-tuned solution synthesis of different systems. For example, you can start with zinc precursor and selenium precursor and react them, and depending on temperature, this system can navigate different pathways on this free energy surface, along this free energy surface, and same material with cubic unit cell will form one-dimensional atomically precise wires or two-dimensional platelets with atomically precise thickness, or something or like more like three-dimensional structures. And that has been best, I think, optimized to date for growing, for finding these valleys leading to two-dimensional structures that have electronic structure of quantum wells. So they're colloidal quantum wells, but they have true atomic precision along the thickness. So we can make, and it's a chemistry, so it's solution synthesis. So you can make grams, kilograms, you can scale it. So these can easily go into commodity materials. And since, and we can here control dimension or size of the structure with true atomic precision only along one dimension, the smallest dimension, the thickness. But in the system, in the strong quantum confinement regime, it is the dimension that fully controls the electronic structure of the system. And as a result, we can make a very materials with very sharp ensemble emission lines and very interesting material systems. But if we want to turn it into a complete methodology for growing like really truly complex structures, or just trying to mimic material complexity of the material systems that people can grow by molecular beam epitaxy, for example, we need to couple this atomically controlled nucleation to ability to grow systems with atomic precision following the nucleation event. And that has been accomplished by taking an inspiration from the process used in pretty much every CMOS semiconductor foundry and almost every clean room, known as atomic layer deposition. So you, in semiconductor technology, we routinely use a process called atomic layer deposition, where you can grow conformal layers of, for example, oxides, and that is used in transistors to grow so-called gate dielectric layers. And the way how you can grow this from gas phase in a very conformal way is to split the reaction into two complementary half reactions, where each reaction is self-limiting. So you grow one monolayer, then you grow another monolayer, then you grow yet another monolayer. And we developed an analog of this process that can be done in solution, not in gas phase. And that allows you to grow heterostructures, semiconductor heterostructures with starting with our atomically precise substrates and then add one layer at a time, atomic layer at a time, and grow nearly arbitrary sequences of atomic layers in solution. And, for example, synthesize like epitaxial stacks of multiple quantum wells separated by barriers that are also engineered with close to atomic precision, so, or more accurately, atomic layer precision. And this is an example of cross-sectional transmission electron microscope image of a triple quantum well heterostructure synthesized in solution. And we have many of them synthesized simultaneously. So, and again, if we need kilogram of these structures, they can be made. And that was probably one of the first, if not the first example of structure of kind of materials that have complex materials grown with close to atomic control. And it kind of brings us one step closer to ultimate goal of that we can formulate as like building digital nanomaterials, where we control systems down to atomic layer. And we can now map physical principles like band gap engineering, interface engineering, strain engineering onto experimental observables like line widths, quantum yields, or G rates, and engineer materials with superior properties. So it's just as a first steps down along these lines is we demonstrated some time ago the ability that we found that these materials can act as an excellent optical amplification, optical gain medium, and for lasing. So we all know that quantum wells are really good materials for lasing. Now we can make them in solution, we can process them. And I want to emphasize the role in the development of this field accomplished by the group of Volkan Demir at Bilkent University. He is, in my opinion, undoubtedly a world leader in nonlinear optics and lasing using colloidal quantum wells, the structures that shown here. So we did some of the early work, and now his group is doing amazing research by transforming colloidal nanoplatelets or colloidal quantum wells into really lasers that can enter the commercial market. Now, we are now going after even more complex phenomena, such as if you have multiple stacks of multiple quantum wells, you can generate new quantum states of matter. You can couple excitations in different quantum wells to same optical field, and we see some early, some spectroscopic signatures of superfluorescent response where the individual quantum wells in our epitaxial stacks synthesized in solution can couple together and act as a single quantum system, preserving phase coherence between, involving multiple chromophores, multiple quantum wells. So, and it's just a kind of first steps of the exploration, because whenever you have a platform for material design, you can make, it typically leads to interesting developments. And, but now let me switch gears. And I'm afraid that I painted too optimistic picture. So it looked like we can synthesize materials with nanomaterials with true atomic precision. So maybe it's the game over and we can we solved all the problems. And not really. So everything that I told you about, showed before, worked for one particular class of semiconductors, so-called 2-6 semiconductors, so-called cogenide semiconductors. And there are many other materials that are equally or even more important, such as gallium arsenide, gallium nitride, and and it's very difficult, if not impossible, to make these materials by solution chemistry. The problem is that you probably you remember that video that I was showing you, a video of synthesis, and that time I didn't show you, gave you full detail. And this flask was preheated to 370 degrees Celsius. He had the solution preheated to 370 degrees Celsius, and this is probably the highest temperature, very close to the highest temperatures that we can achieve before solvent starts falling apart. It's the highest temperature for organic, so close to highest temperature achievable for organic solvents reliably. And if we now compare it to the temperatures that we use for chemical vapor deposition synthesis, for example, of gallium arsenide or gallium nitride, it will be very far away from what we need to achieve in order to get perfect structural perfection of to achieve structural perfection, to heal or anneal defects and grow high quality, like these extremely important 3-5 semiconductors. So it shows you, highlights the limitation of solution chemistry as a field. So we cannot operate at the temperatures that have been previously identified as optimal for synthesis of some of the world's most important electronic and optoelectronic materials. And that led us to think about possible solutions to this problem. And if we can move, if we can make phases by solution chemistry that require high temperatures. And that probably the most thermally stable solvents I can think of would be molten inorganic salts. And we moved in and we started playing with molten inorganic salts as solvents for doing colloidal chemistry several years ago. And to our surprise, it was the very first examples, to the best of our knowledge, of colloidal demonstration of colloidal stability in molten salts. And these are arguably some of the first examples of molten salt, of colloidal dispersions in molten inorganic salts. And in fact, just as a side comment, you probably think that when we think about molten salt, you probably think about something like liquid molten sodium chloride, and that melts at around 900 Celsius. And it's not required to be that high temperature. So for example, there are molten salt eutectics that melt at temperatures like 100 degrees Celsius. So you can even do quite high precision chemistry using this molten salts. And I was asking myself around that time, how comes that this colloidal stability in molten salts has not been discovered like 100 years ago? Because molten salts have been around, small particles have been around, smart people have been around. And the only rational explanation of why it has not been done before to me was that even the fact of stability of colloidal stability in molten salt goes against all our current knowledge of what you need to have a colloidal, to form a stable colloidal solution. The idea here is that if you want to make a colloidal solution dispersion, you need to have pair interactions, pair potentials net repulsive. So your particles or whatever else you have in solution, when the two particles come close together, they should feel repulsive potentials. They should not aggregate. And there will be always attractive component to the potential, van der Waals attraction. And you need to have a repulsive term that is stronger than van der Waals attraction. And that in molten salt, since it's a very polarizable medium, for example, the Debye screening lens, if we define it, classically, it will be on the order of 1 angstrom. It's extremely concentrated electrolyte, and that's why electrostatic repulsion, AA repulsion, will always be inferior to van der Waals attraction. So these colloids should not exist. They should aggregate and fall down at the bottom. And but they do exist. And in the recent years, we try to understand what is going on, and we are doing a lot of computational work and hard X-ray analysis and modeling. So, and the picture that is emerging that in the molten salts, we have a new, qualitatively new type of colloidal stability or type of pair potentials and interactions between particles, between nanocrystals. So in the dilute electrolytes, we are in so-called Debye-Huckel regime, where potential drops exponentially into the solution. But if you move towards molten salt, extremely dense concentrated electrolytes, you switch to a different regime, which is based on long-range ion correlations, and potential is now not exponentially dropping into the polarizable medium, into electrolyte, but starts oscillating. And you have a transient layering of cations and anions next to the surface, and that we can see in a frustrated Ising model analysis, or we can see in molecular dynamic simulations. And what is most important, we can see also this effect in hard X-ray pair distribution function analysis studies. And so it looks like this surface templated restructuring of molten salts is emerges as a new type of colloidal crystallization, and that's work in progress. Of course, there is a lot of puzzling pieces here, but let me maybe jump to practical aspects of it. What can it do for a synthetic chemist? And there are many systems, as I already mentioned, that cannot be synthesized by solution chemists, or could not be synthesized by solution chemists, despite numerous attempts over past 30 years. And examples of these materials would be some gallium arsenide, gallium and ternary systems like indium gallium arsenide, indium gallium phosphide. And those are important materials, like world best lasers made out of gallium arsenide, or indium gallium arsenide in gas is a best material for near infrared applications, and so on. And in molten salts, in traditional solvents, this chemistry doesn't work. Temperature needs to be too high, also chemical compatibility issues. In molten salts, we can turn all these problems off and make first examples of materials, high quality materials with composition in indium gallium arsenide, indium gallium phosphide, and gallium arsenide compositions. And why we are excited about it? Because, for example, now the quantum dots are materials, commercialized materials used in displays, like Samsung is selling a huge number of QLED TVs every year. And these materials are using indium phosphide quantum dots as color converters. And indium gallium phosphide is a more thermodynamically stable phase. It's a beta phase, so we are now working together with Samsung to evaluate if these materials, new materials that have been sensitized in molten salts, can be a better option for TV market. And it's in general, I want to emphasize that 3-5 materials, in my opinion, of course, is a way to go, because these materials are well, superseded and all other semiconductors in every market, electronic and optoelectronic market, if we talk about performance. Like if we think about, this is a famous chart of records solar cell efficiency for different materials. And this is a semi-legitimate way to compare all kinds of semiconductors, like 2, 6, 3, 5 perovskites and unconventional organic semiconductors, because solar cell is a demanding device. It's a minority carrier device that requires a lot of, well, ultimately pushes semiconducting material to the limit in terms of its capabilities. And the upper half of this chart is exclusively the world of 3-5 semiconductors. And I'm very excited to see the first glimpse of success with using molten salt for synthesis of previously inaccessible 3-5 semiconductor, especially in form of quantum dots, because solution synthesis is very scalable and it can drive cost of these materials down, and eventually we may be able to engineer very complex and unusual material systems using solution chemistry. The other area where molten salt seems to made a big progress in recently was engineering of relatively young class of two-dimensional transition metal carbides and nitrides known as enzymes. And these are two-dimensional materials that can be made out of many different early transition metals, such as titanium, chromium, molybdenum, vanadium. And these materials are used in, already set a number of records for energy storage applications, such as supercapacitors, batteries, materials for electromagnetic shielding, and composites, catalysts. And what makes them special? I'm sure all of you are very aware about two-dimensional materials, the world of two-dimensional materials, a very hot topic. And when we think about 2D materials, we typically imply graphene or molybdenum disulfide and other materials that do not have any any possibility for surface engineering. And Enzyme in this respect is unique because it's a 2D material with surface chemistry. So each surface atom has chemical access to, can be accessed chemically and form equivalent chemical bond that can be used to attach different groups and control chemical reactivity, stability, properties like energy storage properties. And for many years, it has been realized, it has been recognized that, yeah, it should be possible to engineer surfaces of enzymes, but the chemistries that we had in hand for these materials did not allow us to do it. So like typically the surfaces of enzymes have been a rather random mixture of hydroxy, oxo, and fluoro terminations that come out of like synthetic process. And more, last year we implemented the molten salt chemistry that again allowed us to do reaction in solution on one hand, but on the other hand, push it to the temperature domain where that you wouldn't be able to accomplish with traditional solvents. And now we can do surface engineering reactions, and we made about, in that paper, we reported about 20 new enzyme structures showing that these materials can be superconductors, we can control their mechanical properties, elastic properties, and so on. So it's, again, just another highlight showing that chemistry, solution chemistry in molten salts is an interesting avenue that may enable all kinds of new material systems and new applications. Now let me switch gears and briefly talk about, well, to moved beyond the engineering of individual nanostructures. So I've been talking about nanoparticles, now enzymes and these are, we can consider them as the functional bricks of nature, that they are the smallest units that carry function, like a metal or semiconductor. If you have like one gallium atom and bonded to one single selenium or arsenic atom, it will not be gallium arsenide. You need to have quantum mechanical coupling over about 100 atoms or so to develop like the key aspects of the band structure or electronic structure of a semiconductor, gallium arsenide, for example. Same applies to metals, same applies to magnets, same applies to other material systems. And in many ways, nanomaterials are these functional bricks of nature. Bricks, the smallest brick of a semiconductor, the smallest brick of metal or catalyst or magnet and so on. Now we can, Now we can, next question is how can we build with these bricks? So whenever, we think of building blocks, how can we use these materials as a building blocks to build something bigger or complex? And here we rely on, we can again draw this analogy of nanomaterials, nanocrystals as macromolecules. So if we have macromolecules and if we can disperse them in a solvent, for example, we can then crystallize out of the solvent macroscopic assemblies of these structures, and we can grow superlattices of individual nanoparticles, for example, nanocrystals. So we can first put atoms in form of like 100, maybe sometimes 1,000 atoms large bricks, and then we can put many of these bricks together, and we can grow crystals of nanocrystals, or we can combine 2 or 3 components, and they will grow even more complex structures. Something like, sometimes it can be truly amazing in terms of complexity, where we can pack different functional building blocks into structures, extremely complex structures. And it's these units, this packing of nanoparticles formed spontaneously is isostructural with intermetallic compounds. It's a type of the units, so like sodium chloride type structure, for example. So it's like calcium copper 5, but instead of calcium, we have a 10,000 atom unit of a semiconductor, and instead of copper, we have like 8,000 atom large unit of a ferromagnet or catalytic material, plasmonic material. And we can grow different structures, they can pack together, and they can form amazingly complex assemblies, amazingly complex structures, not only crystalline sometimes. Sometimes, this was the first example, like this structure is the first example of quasi crystal. So this is quasi crystals are the material, the structures that have long range order, but they don't have translational symmetry. And in this case, you can have, for example, symmetry forbidden elements, like, for example, rotational symmetry axis of order of 5, 10, 8. This structure has a rotational order of 12th order, it's C12. And it's one of the most amazing structures, and it can be mapped onto square triangular tiling, and it's material that doesn't have periodicity, but if you take a X-ray diffraction of it, it acts like a perfect crystal with symmetry elements that crystal cannot have. Well, anyway, it's a very interesting story on its own, but I want to now move towards some more practical comments and ideas. So again, I showed you a very optimistic picture. We can make different, very complex building blocks. We can pack these building blocks into amazingly complex structures. And how can we turn them into functional materials? And here there is yet another caveat. And I want to emphasize, like when we start making this, building these structures for the first time, we hoped that within a couple of years we will be able to largely like rewrite solid state physics textbooks by building materials like from building blocks, coupling, developing new band diagrams and so on. And well, we used like an inspiration, this idea that if you have like sodium and chlorine and put them together, you form sodium chloride that looks very different from sodium and chlorine. And you develop a whole new electronic states. And it's not happening here in these type of structures. And the reason is because in addition to making amazing building blocks and packing them into very interesting and complex structures, you need one more component, which is connection of coupling, electronic coupling between the components. So the wave functions in individual structural units should talk to each other and form a very strong exchange coupling. And you can describe it within different theoretical frameworks. For example, you can use tight binding model and look at the magnitude of the resonance integrals beta. And the problem now, it's not about particles, it's not about their packing, it's all about what is at their surfaces. Because if you have at the surface a layer of electrically insulating ligands, they will form a bilayer that will introduce insulating barriers between individual particles. And electronic states will not be able to delocalize. So they will be strongly localized on individual building blocks, and our imaginary sodium chloride will be a linear combination of sodium and chlorine. So just there will be no new states developing. And that's a big challenge. And we spent about 10 years working along these lines to solve it. But, and we had to completely rethink the idea of how we engineer surfaces and surface ligands and surface interactions. And that led to the development of the concept of inorganic surface ligands for nanomaterials. So we developed, we and others, of course, now many people joined this field and did amazing work along these lines. But the idea here is how to design something that will be able to provide colloidal stability. So we can make materials and handle them in solution. But after you form a film, you form active components of electronic and optoelectronic devices, how can you make neighboring nanocrystals, individual nanocrystals talking to each other? And that you can do it through engineering, different types of engineering of surfaces and using inorganic chemistry, inorganic methods. And that led to very significant improvements of coupling, like for example, conductivity of gold nanoparticles with organic ligand. If you compare it with gold conductivity of same particles with inorganic ligands, the difference will be about on the order of 12 orders of magnitude. So it's a huge effect. So it's a huge improvement of coupling, and materials started entering into so-called strong coupling region. And that leads me to more like practical aspects of what these types of materials can be good for. And there is a big excitement and interest to turn these materials into a universal class of optoelectronic materials for where we can start with inks, nanocrystal inks, and rely on solution deposition or printing or other methods and involving mild processing, and make active components of electronic and optoelectronic devices. It's important to be realistic here. So I don't want to make any misleading claims that such materials can outperform silicon, where silicon is at its best. Probably not. But we can do things that silicon cannot do. And we can do it in a way that will complement the weaknesses of, or address the weaknesses of existing materials platforms. Like, for example, if we want to couple these materials with flexible substrates, if we want to couple them to optoelectronic readout circuits, for example, silicon will never be used as a material for infrared applications because it's just transparent in the infrared. But we can make we can use CMOS circuitry to build readout circuit and cover it with a layer of quantum dots that are specially designed to interact with infrared light, generate electron-hole pairs, and turn silicon into infrared detector, for example. And you also cannot make laser out of silicon because it's indirect via semiconductor, but we can complement it with quantum dots that are direct gap, really good. And this idea of cross-platform integration is a very powerful concept that can be implemented with quantum dots. And overall, there is a lot of work these days, both within academia and in industry, exploring practical applications of nanomaterials. And here I'm talking about one small subset of nanomaterials, quantum dots, semiconductor quantum dots, for real world applications. And one big area led by companies like Samsung, TCL, and Philips, using quantum dots in light emitting diodes. And these materials are viewed as a big competitor and legitimate competitor to OLED technology, organic LEDs. And if you look a little deeper, it's actually OLEDs and QLEDs are not different technologies. They use same device stack, and it's just different chromophores. So eventually, within industrial communities, there is a belief that eventually these two fields can merge, and we may use quantum dots for one type of pixels, organic chromophores for the other types of pixels. The other area where these materials can be very interesting is infrared and near-infrared detectors, where you can make your inexpensive CCD camera sensitive, or CMOS camera chip sensitive to infrared. And there is a lot of interest from smartphone manufacturers for this. There is a lot of interest within energy technology domain, solar concentrators, solar cells, and even agriculture. It turned out that these materials are very potentially interesting for agricultural applications. And the idea is the following. So leaves are green because they have chlorophyll has an absorption band in the orange-red part of spectrum, and they have an absorption deep in the green. And if you in the greenhouse install these layers where quantum dots, and here you need to look for non-toxic quantum dots, of course, and inexpensive in polymer matrix, and they can be designed, these layers films can be designed that they absorb full sun spectrum and convert it into red-orange light that is spectrally tuned to the absorption band of chlorophyll. And that, based on current experiments, studies, it significantly increases the crop yield. And so you see, it's a huge parameter space to innovate from the practical points of view. And my lab spent quite a lot of time working on different all-inorganic nanocrystal devices, implementing ideas that we developed for surface engineering to achieve good electrical conductivity. And within this domain, nanocrystals can be used for solution processed solar cells, thermoelectric materials, optical gain media, and field effect devices, infrared detectors. And again, by any means, I don't want to say that it's a small community, especially now when industrial players join the game. There is a growing consensus, or probably already established consensus, that these materials, semiconductor quantum dots, do provide a versatile and competitive platform for optoelectronic devices. And the state of the art is that at the level of individual device, like single LED pixel or single transistor or single detector pixel, we are very competitive. The field is these materials are very competitive to other optoelectronic materials, especially solution processable. But that's not where we want to be ultimately. we want to move towards the systems level. So nobody cares about, well, the market for a single LED pixels, single LEDs are much smaller than the market for displays, for example. And same, you don't need, except very niche applications, individual infrared detector pixel, you want to have a camera, infrared camera. And that brings me to the next level. And that was a missing part a few years ago when we looked into this. So we need to find the ways how to not only make devices, individual devices out of semiconductor quantum dots, but also how to make complex systems, how to pattern them. Like realistically, if we draw analogy with silicon technology, what made Moore's law and modern optoelectronic, modern semiconductor electronics possible is development of and evolution and of lithography. And well, that the next part, the last part of my talk today will be about what we call dolphins, and it's the method that our group has developed a few years ago called direct optical lithography of functional inorganic nanomaterials, so Dolphin. The idea was that if you have solution materials like quantum dots, you want to pattern them, you want to make a complex circuitry out of them or array of display pixels, you have different, you can use different methods. You can do inkjet printing, you can do transfer printing, and every method has advantages and disadvantages. And it's very important to be, again, realistic about what one technique can do and what other technique can do. And in many ways, there are many great things about, for example, inkjet printing, but resolution-wise, it's very difficult and probably, well, based on current understanding of industry, maybe nearly impossible to scale below the resolution on the order of 10 microns or so. And speed, it's a sequential, so you print like element by element. And if you need, let's say, a display to print a display, which has about 100 million subpixels, it sounds like a challenge. And on the other hand, in modern semiconductor technology, we heavily rely on lithography. Lithography used photopolymers that used as photoresists. And then if you make a layer of photopolymer, you can expose it through locally through the mask to UV light, and this exposure changes chemical properties, and you selectively dissolve exposed or unexposed regions. And then you can deposit and pattern materials. And that works very well for vacuum deposition techniques. For solution deposition, it turned out like for quantum dots, it turned out to be not particularly efficient for two reasons. First of all, capillary forces redistribute material when you have a layer of photoresist with opened windows, and then you spin coat, let's say, a layer of quantum dots or other solution processable materials. There will be huge capillary forces. And photopolymers often swell in solvents, and there are technical challenges. And we developed, to address these challenges, we developed a cousin to traditional photolithography that we call Dolphin. And the idea is to avoid using photopolymers, photoresists, but instead use design surface chemistry of nanoparticles to act as photoresist. So the idea here is that we can coat a layer of quantum dots and then expose them, and then exposed or unexposed regions, depending how we design the chemistry, will allow us to remove selectively exposed or unexposed areas. And then when we repeat it multiple times, we can make in parallel, like what makes photolithography such a powerful technique is that it's a huge parallel process. And you can define billions of circuit elements in a single step. And so that's something that now we can do with quantum dots, and that is that required a bit of chemistry. So we designed different surface chemistry, surface engineering of chemical engineering of particle surfaces, utilizing different chemical strategies. One of the strategies can be so-called photoacid generators that are used in traditional photopolymers, but now we specially design them to interact with nanocrystal surfaces. You can also use some different types of surface ligands, and in this case, we designed surface ligands that molecules that you attach to the nanocrystal surface. When you illuminate it with light, it just undergoes excitation, optical excitation, and that leads to photochemical decomposition. It just falls apart. And there are many other methods, in fact, that allow you to engineer to make nanoparticles photochemically patternable using either deep UV light or eye-line radiation, or even very inexpensive of 400 nanometer radiation. And in this case, again, it's very important. There is no solution that fits all needs. So it needs to be tailored to particular technology, to particular limitations, particular restrictions, and sometimes cost is a limitation. And then we can use very inexpensive materials and inexpensive patterning techniques. Sometimes resolution is a limitation, and then we sacrifice cost, but go after more sophisticated methods. Like, for example, we can use E-beam, electron beam patterning to make a really, really high resolution, directly patterned inorganic nanostructures. But I think what is exciting is that this type of chemistry works, or this type of approaches like Dolphin works for pretty much every material that can be synthesized by solution chemistry, like metals, oxides, semiconductors. Most recently, we published a work when we photochemically patterned perovskites, and many other materials. And practically you can do it for designing of optical photonic elements, and optical gratings, for example. You can pattern field effect transistors. You can pattern optically transparent field effect transistors, for example, to drive individual pixels of LED screen. You can pattern something that probably most recent work, and something that I believe may be really important, is there is a big challenge in patterning quantum dots for certain types of displays. And in displays, the type of technologies that you want to use during the manufacturing workflow depends on what display, what is the form factor of your display. Like if you talk about huge displays, like large screens, the subpixels typically on the order of 100 microns in your TVs that you have at home. And that size, for that size, you probably should rely on inkjet printing because it has many advantages in terms of material usage and so on. But if we go towards displays for small applications like smartphones, consumer applications like IR, VR applications, micro displays, where display is tiny, the subpixel is smaller than 10, so it's significantly smaller than 10 microns, and it cannot be printed. We need to look for different methods, and we just recently reported a method that allows patterning, high resolution, like micron and submicron patterning of pixels of active operational quantum dot light emitting diodes. And well, to summarize, it's kind of building and growing that what we can call like Dolphin ecosystem. So we develop different chemistries, apply them to different materials. We can push resolution. We are now moving into 3-dimensional, 3D patterning. We are patterning active devices. And again, now, well, when we started working in this field around 2016, there was pretty much no work done. It was not recognized as an important technological challenge. But now there is a lot of work, a lot of competition, a lot of active development, and very clever ideas coming from community, both in academia and in industry. And now let me wrap up my presentation and just move to the summary to remind you what I've been talking about. And we talked a little bit about chemistry, how to synthesize, how to do very high precision synthesis of different nanostructures, how to pack them in super lattices, how to engineer their surfaces using inorganic ligands for nanoparticles, for MZNs, and then we talked a little bit about photolithography, or direct optical lithography of nanomaterials and Dolphin. And now let me move to the most important slide of this presentation. I want to emphasize that the work that I've been talking about has been done by a great team of students and postdocs working at the University of Chicago. And I want to acknowledge the role of multiple collaborators we had privilege to work with over the years, and thank the funding agencies that kept us afloat for all these years. And thank you for your kind attention.
Thank you, Dmitry. Thank you very much for this very deep, comprehensive, and inspiring talk in the spirit of our seminars. That was a great pleasure to listen to it. So can we now pass to Q&A session, taking some questions?
Absolutely. Do you want me to stop sharing screen, or should I keep it?
Yeah, maybe, as you like.
Okay.
So please ask questions. Send in a message through chat button or just by raising hand. Dmitry, perhaps I can ask the first questions. Participants are preparing questions I can ask directly. Have you tried to construct using this functional Greek metamaterials?
Are you talking about optical metamaterials? Metamaterials is a very broad field. One area that we are currently exploring and working on is to use Dolphin type methods for building meta surfaces for so-called meta optics, where by designing, by patterning like dielectric coating, you can spatially control phase of electromagnetic wave, and just build lenses and build other optical elements that are strictly two-dimensional, like 2D. This field is called 2D optics, and or 2D photonics. And the idea here is that, in fact, in principle, it's possible. There is a legitimate theoretical foundation showing that you can engineer such materials. Like you can make a lens that are strictly two-dimensional. And the reason why it's very important, because actually, if we talk about cell phones or other consumer products, some of the most expensive part of the stages of technological workflow, manufacturing workflow, is to implement, you can do amazingly complex chips, like electronic silicon chips. But if you want, then you need to combine them with lenses, for example, for CCD cameras, for cameras that you use on cell phones. And that's extremely expensive. So if you can make lens building, if you can build lens as a part of the chip manufacturing, like you make a readout circuitry, you put on top material systems, layers that act as lenses or other photonic elements, it's a huge challenge and huge opportunity for optoelectronics. So that we are working on. You need to be able to pattern materials with very high resolution, down to about 200 nanometers, and it is pushing the limit of Dolphin. So we are learning how to do it, and it's it's a work in progress.
I see. Thank you. Thank you.
Well, can you comment? I received a question. Can you comment on the stability of these systems? Well, it's a very broad question, and again, depending on what materials you're talking about, it's well, if you talk about quantum dots, they depend what you're comparing them to. Like one reasonable or legitimate competitor to nanomaterials are organic molecules, like organic dyes or laser dyes. Quantum dots are more stable. They have been in the early days, they have been introduced as a higher stability, more stable replacement of organic chromophores, of organic dyes. If we talk about device stability, like for example, lifetime of OLED versus QLED, currently OLEDs are better. And the reason the belief is, at least within industry and academia, is that just we are about 10 years behind. This field is quantum dot field is about 10 years younger than OLEDs. And if you look into what OLED community was doing during the past 10 years, was working on improvement stabilities. So we are trying to learn, we are trying to catch up and reduce the gap. And intrinsically based on how we understand the degradation mechanisms, nanomaterials should be better. And yet to be shown, because many technical aspects need to be solved. So there are examples of nanomaterials that are not stable or experience serious stability issues. And metal halide perovskites is one of those that need to be, well, the community is currently exploring how to make them more stable. Yeah, it's a very broad question.
Thank you. Also, John, please come.
Yeah, actually, I just type on the chat area this stability question. This solution chemistry is really attractive, but I see the one issue is this stability. That's why I just raised that question.
Okay. The next question. Please go ahead.
Thank you for the answer. Yes.
Now, there is a question, is classical thermodynamics sufficient to describe the dynamics of quantum transport in such nanomaterials, or generalized thermodynamics, non-Boltzmann statistics are needed? Well, transport in nanomaterials is, if you're talking about electron transport, has been analyzed and studied using different frameworks, theoretical frameworks. And in the past, when we had materials with low electron mobilities, they could be very accurately and impressively well analyzed and modeled by Hopin transport, or more specifically, Shklovsky variable range Hopin transport. And now we are entering with improved materials. We have mobilities that cannot be described by Hopin regime, or at least we cannot. And then we are entering into rather complicated and heavily debated area of how to think about transport and at the cross over from localized transport to delocalized transport. There are multiple theories, transient localization theories. There are theories based on polaron, like a small polaron, medium polaron, large polaron picture. And it's a very interesting and, again, challenging frontier in physics, in the physics of granular electronic systems. And they invoke a lot of physics, like modern physics that people received Nobel Prizes for, like Mott metal insulated transition, Anderson localization. All this is at play there. And we can even engineer systems to move them from one regime into the other. it's an extremely interesting field, and a lot of very interesting science is done these days. And well, another question is fractal structures in nanomaterials, if there are any, such as self-similar structures, play important role in the dynamics? Well, definitely fractal dimensionality is a very common effect to see in nanomaterials, and especially nanomaterial aggregates. And it's like the first example that comes to my mind is a very interesting work on aerogel and nanoparticle aerogels, and where this fractal dimensionality was utilized to make materials kind of open, very low density, and for interesting catalytic properties. And some of the best work, to my knowledge, was done by Professor Alex Eichmüller at Technical University Dresden. And yeah, so it's definitely possible. And something why I'm so excited about nanomaterials, that it's such a versatile field that you can, if you work in this domain field for many years, you can touch almost every aspect of modern physical sciences and probably biological sciences. And okay, let's see, like another question, would it be possible to extend Dolphin to 3D patterning techniques? I think yes, especially using 2-photon lithography, yes, it should be possible. We didn't do this, but we thought about it for a number of years, and I think it's a great opportunity. If you are interested, please step by and do it. And another, I'm wonderful if there is the highest temperature that can be reached within molten salts. And is there any semiconductors that you want to synthesize below this temperature limit? Well, I think it should be not a problem to achieve high temperatures using molten salts, because they will not break apart, they will not chemically decompose. The problem is that it's difficult to maintain particles without sintering and without aggregation or growth through ostler ripening at very high temperatures. So we are currently kind of fighting with a compromise that, well, for 3-5 materials, for 3-5 semiconductors that we are working with, the optimal temperatures that we use are in the regime between 400 Celsius and maybe 550 Celsius. So occasionally we would like to go higher to higher temperatures to explore even those even more extreme conditions, more extreme situations. But for 3-5 semiconductors, it's not molten salt, but the semiconductors themselves start undergoing unwanted chemical transformations. And it's such an early field and such a different from all other activities. So we need to learn how to control this process and even what determines stability in molten salts at high temperatures. But molten salt itself, I don't think is a limitation from temperature point of view.
Thank you.
You're very welcome.
So, more question, please. So it seems that there are no more questions. Dmitry, perhaps if you want, please give your final comments, and then we can close the session.
Okay, well, thank you for the invitation, and come to you. Well, if you are interested to have a great career, especially for young scientists, think about University of Chicago. It's a great place, one of the best places to study or work, and we are looking for talented people, and I would like to express a welcoming note to consider University of Chicago as a place to do science. And I'm very impressed about science that is done in your country. Again, some of the best work in nanoplatelets for synthesis and lasing, and very recently there was a very beautiful work on patterning of nanoplatelets for lasing application was done by Volkan Demir at University of Bilkent, and I saw many other great works coming from Turkey these days.
Thank you so much. That was a great pleasure for us. We will be also waiting for you in person to take participation in our summer schools on other activities, or just as a visiting science. So when this coronavirus situation will be resolved finally. So for the time being, please take care of you, and we hope to meet you in nearest future here in our country.
Absolutely. Thank you. Thank you for the invitation.
Thank you. So bye.
Bye. Good night.
Good night. Good.